In this second video for section 4.3, we're going to talk about a theorem that sometimes makes determining whether a set is linearly dependent or not a little bit easier. Here's the theorem. A set of two or more vectors in a vector space, so this is any vector space, polynomials, Rn, could be anything, is linearly dependent if and only if one of the vectors is a linear combination of the other vectors. So I'm not going to prove this. If you want to read the proof, it's on page 231 in your textbook, but I do want to take a quick look at a couple examples so that we can understand how this theorem works and what's going on behind the theorem. Let's start with just a set of two vectors. What happens when a set of two vectors, v1 and v2, is linearly dependent? Well, that means that this equation holds, c1v1 plus c2v2 equals 0, and one of these two scalars, c1 or c2, is not 0. Since it doesn't really matter which order we put these in, right? We can rearrange addition however we like. Let's just assume that this one, the first scalar c1, is non-zero. What that does is allows us to divide through on both sides of this equation by c1 to get this new equation. So v1, and really I should have a line over v1 to show that it's a vector. v1 no longer has a coefficient written out. There is a 1 coefficient there, but we don't usually write that. And now both of these coefficients, the c1 and c2, have been moved to appear on v2. The reason why c1 can't be 0 when we're doing this is that we can't divide by 0. And now we can do one more rearrangement. Let's move this, v2 and its scalar, to the right side by subtracting, and we see that v1 is equal to a scalar multiple of the second vector. So this is the simplest kind of linear combination, just a scalar multiple of a single vector. Things get slightly more complicated if there are three vectors, like there are in the next little example. So suppose this other set with v1, v2, and v3 is linearly dependent. So that means we have the same equation with an extra vector, c3, v3, and it's set equal to 0. And we know that at least one of these coefficients is non-zero, so let's just go ahead and assume again that the first one, c1, is not 0. Now divide through on both sides of the equation by c1. We get this new equation. And now move this term and the third term to the right to get this final equation. And we can see that v1 is equal to negative c2 over c1 times v2 minus c3 over c1 times v3. So what we're looking at is v1 is a linear combination of the other two vectors. So our linear combination is maybe a little bit complicated to look at because of this division, but really negative c2 over c1, that's just a number, and negative c3 over c1, that's just a number as well. So this is a linear combination. So if you wanted to prove the theorem that we're considering, you would have to do it in a little bit more generality. You would have to start with a set of any number of vectors, maybe v1, v2, up through vm, and then prove through this same kind of manipulation that one vector is a linear combination of the others. To wrap up this section, I want to take a look at two theorems. I'm not going to prove either of these theorems, and the proofs are in your textbook, but I want you to take an attempt at proving these theorems on your own before you check the proof given in your textbook. And I have a couple little hints for you. So the first theorem says that if we have a vector space V, then any set of vectors in V containing 0, and this is the 0 vector of V, is linearly dependent. And my hint for you, when you try to prove this on your own, is to think about what the coefficient of 0 should be when you write out the equation like we have in the definition. So you would want to set up this equation. One of your vectors is going to be 0 when you're proving this theorem. And then think about the coefficient on 0. And once you've given that a thought, you can check the proof in your textbook. Here's the second theorem. If we have a set of vectors v1, v2 through vm that are linearly independent in the vector space V, then any set containing these vectors v1, v2 through vm is also linearly dependent in the vector space V. And here's my hint for you. You're going to need to use this equation. So I have a linear combination of the original set of vectors, set equal to 0, and we know that this has a solution where at least one of these vectors has a non-zero coefficient. So you're going to need to use this fact when you look at your other set. So when you look at any set containing these, keep this equation in mind when you're trying to prove that that set is linearly dependent. And again, after you've given it some thought, maybe tried out the proof on your own, you should go take a look at the proof in your textbook on page 233.